In example 4, we have Maria, who has done some research to find that the mean household salary in the United States is $72,641. That those salaries are right skewed, so you might think about what that looks like. Remember, this direction of the skew is where the long tail is, so right skewed means the data has a long right tail, which basically means that most people have sort of lower salaries, but then there are a small proportion of people who have much higher salaries than everybody else, and that those few people's high salaries create that long right tail, and they pull the mean up. So the mean would probably be higher than the median household salary because of that right skew. Those few high values influence the mean and make it higher than it would otherwise be. All right, and the standard deviation of household salaries apparently is $26,145. So her question is whether people in her area of the country have a lower average salary than what it is for the country as a whole. So she collects data from a random sample of 1,500 households, and her sampled group has a mean household income of $54,398. Now again, before we do any of the parts of the example here, let's just think big picture. Her sample mean is definitely lower than the U.S. average, but the question for us is whether that kind of sample mean could just happen due to the random nature of sampling. In other words, even if the average for the whole country is $72,000, if somebody takes a sample of 1,500 households, they may not get exactly that mean. So we expect some variabilities in the means from different samples because each random sample has a new set of 1,500 households, but we'd like to know if a mean of $54,398 is sort of typical, even if the true mean for everyone in the whole population is 72,000. Okay, so the research question for Maria's study is the mean household salary in her area of the country, household, less than the national average, which again is 72,641. So that's her question. And again, it says she wants to see if people in her area of the country have a lower mean salary. Right? So the population that she's trying to understand something about is all, well, I guess we should say households and not people. All households in Maria's area of the country. So, in general, when we compare population to sample, we think about the population as being sort of the all, and the sample as being the small. So the sample is a subset of the whole population. All right, then it asks about the shape of the population distribution. And it says here salaries in the U.S. are right skewed. And then it asks, is her data categorical or quantitative? So in order to answer that, we should know what the variable is. And actually, we should think about what the observational units are. So who or what is Maria collecting data from? In this case, it's households. And what piece of data is she collecting from each household? It's their income for the household. and that's measured in dollars. Notice that it's not average household income. The variable, what she is collecting from each household, is the income of that one household, not the average income, just the income for that one household. And then she collects 1,500 different incomes from 1,500 different households, and then she adds all those 1,500 incomes together and divides by 1,500, and she gets an average for her group of 1,500. But from each individual household, she collects one household income. So that's the variable, which is quantitative. It's something that's measured. It has units, not categories. So that would be our clue. Now, knowing that our variable is quantitative, our parameter then has symbol mu. And mu is the average of whatever the variable is, and it's again about the all, right? So the average household salary for all households. The parameter is about the whole population for all households in Maria's area of the country. So whenever we're describing the parameter, we started the semester with parameter pi when we had a categorical variable, and our description always started with the long-run proportion. And the description was the long-run proportion of whatever success was in that experiment. Now we've expanded on that. So even when our variable is quantitative and we're using pi for our parameter, it might not be the long-run proportion, but it might be the population proportion of all observational units and their value for the variable, right? So in this case, the observational units are households. Mu is a parameter that's describing something about all households in her area of the country, and what she's collecting data on is household income, and so mu is the mean, the average household income salary for all households in her area of the country. And the value, as the second question asks, of mu is unknown. So in general, we don't know the value of any of our parameters, right? We make an assumption about the value of the parameter to create our null hypothesis, but we don't actually know what the true value is. Okay, so now we want to create our null and alternative hypotheses. I'm going to do the symbols here. The null hypothesis, we're going to assume that mu, in other words, the average for all the households in Maria's area of the country, is the same as it is nationally, which is 72,641. So again, this null hypothesis is not really about random chance. It's about what is true in the whole population and what we're going to assume. So we're going to start by, let's assume that for her area of the country it's the same as it is for the rest of the country. And then her alternative research conjecture is that in her area of the country, the average household salary is actually less than it is nationally. So we're using the less than symbol to go with the less than that we had previously in the research question in part A. Now, if we wanted to write these hypotheses in words, this is one of the reasons why we like using the symbol mu for all those words in part D, because then we don't have to write all that out, right? So in words, we would just copy from part D everything that mu is equal to. The average household salary for all households. So the word all is so important in this sentence because this hypothesis is about the whole population, not just the sample of 1,500. All households in Maria's area of the country. that average is 72,641. That's the null hypothesis assumption. We don't know for a fact that that's correct, but we're going to assume it to be able to do our analysis. And then the alternative, all right, stop. Hey, stop. Sorry, my dog is growling. The alternative is that the average household salary, again, of all the households, so we're talking about the whole population when we're making our hypotheses. For all households in Maria's area of the country is actually less than it is nationally. So we'll say is less than 72,641. So again, it's really nice to have that symbol mu that can stand in for that whole big long sentence. Really saves us time in writing and lets us write things more concisely. Just remember, the hypotheses are about the whole population. The parameter is describing something about the whole population, not what happened in the sample. All right, now we're going to go to the one mean applet, and we're going to conduct a simulation, and I'm going to show you how to do that. So, I don't know why this is. So we're going to math.hope.edu/ISI, and in the applets, we're going to the one mean applet. And then we're going to click at the top on population model, and we're going to put in the mean 72,641 that we're assuming. We don't know for sure that this is the population mean, but we're going to assume it for the purposes of this analysis. And then I got to go back and look at what the standard deviation was, 26,145. So I'm going to put that in for the standard deviation, 26,145. And the population shape is skewed right. And I didn't have to click on set population. You shouldn't have to either, but you can if it doesn't update the way it's supposed to. So you see the shape of this right skewed distribution. The hump is on the left. It's the long tail that's on the right, and that's what makes it skewed right. So most of the incomes you see are down in the lower range of $30,000 to $90,000, and then there's a few that are higher, say higher than 100,000, 120,000, 150,000, and higher than that. All right, so we're going to click on Show Sampling Options, and we're going to just take one sample to start, and the sample size is going to be 1,500 because that's the size of the sample that Maria took, and we're going to click on Draw Sample, and we get one sample here. Now notice the mean of this sample is 72,037 and the standard deviation is 26,415. So the shape of this sample, the sample is the graph in the middle here, most recent sample. The shape is right skewed. The mean is similar to the population mean, and the standard deviation is similar to the population standard deviation. So basically, when we take a random sample from a population, we get something that looks like the population. It has the same shape, it has a similar mean, and it has a similar standard deviation. Now what I'm going to do, so I don't keep flipping back and forth, is I'm just going to write down what this mean is, and if you have another screen available, or you can temporarily pause this video and go to the applet and do the same thing that I just did and pull out one sample, then you can write down the mean and the standard deviation that you get in that middle picture. Now there's another graph starting on the right hand side of the screen. We're going to get back to that in a minute. I'm going to draw another sample, so I just clicked on Draw Samples, and now I have a mean of 72,804, and I have a standard deviation of 26,695. So again, notice, this is a new sample. It's a new set of 1,500 values pulled from the population. It has a right-skewed shape like the population does. It has a mean that is similar to the population and a standard deviation that's similar to the population. Now the mean from this sample is moved over to the graph on the right, so now there are 2 points there, one from the first sample, and if I touch that, then I can see sample 1 in the middle graph, and if I touch the other square, I would like to call it a dot, but technically it's a square, then I will see sample 2. All right, I'm going to draw another sample. Now I have a mean of 72,032 and a standard deviation of 24,840, and I'm writing this down. I'm going to go back to my sheet in a minute. So notice in this sample we have a right-skewed shape, a mean that is similar to the population mean, and a standard deviation that's similar to the population standard deviation. And now the mean from this sample has gone over to the graph on the right. And I'm going to draw another sample, and now I have a mean of 73,650 and a standard deviation of 27,157.251, and again a right-skewed shape. And the mean from this sample has gone over to the graph on the right. It's highlighted in blue, but I can click back on any of the other dots in that right-hand graph, and I will see the sample that mean came from. And then I'm going to draw one more. So this is my 5th sample, and I see a sample mean of 72,028 and a sample standard deviation of 25,599. And again, a right-skewed shape. All right, so temporarily, let's go back to the worksheet. And again, it's actually really important that you also do this for yourself. So if you have not, I would pause the video, go to that one mean applet, set up the population model, and do the same thing that I just did and write down your results. So my first simulation, my sample had a right-skewed shape, and the mean of that sample was 72,037, and the standard deviation was 26,415. I wrote all these down so I could make a note. The second simulation, the sample, that middle graph, was right-skewed just like the population graph was, and the mean was 72,804. And the standard deviation was 26,695. And then I took a third sample, which was also right-skewed. Right, the graph on the left, notice, was not changing. It stayed the same throughout. That's the population, and it doesn't change. But each time we took a new sample, it changed a little bit. I'm getting a slightly different mean. I'm getting a slightly different standard deviation each time. But generally speaking, each time I get a right-skewed sample, so it looks like the population in its shape, and I get a mean that is similar to the mean in the population, and I get a standard deviation that's similar to the standard deviation in the population. And for my final sample, it was once again right-skewed and has a mean of 72,028, so again similar to the population mean, and a standard deviation of 25,599. Okay, so when we look at this table, every time I took a sample, it was right-skewed in its shape, and that's the same shape as the population. And every time I took a sample, the mean I got was similar to what the mean is in the population. And every time I took a sample, the standard deviation of the sample was similar to the standard deviation of the population. So my samples, I would say, are representative of the population. They look like the population, they're just smaller, but they're like a mini-me of that population. Now, obviously, part G, we can't discuss the results with your classmates, but every time somebody takes one of these samples, it's always going to be right-skewed when the population is right-skewed. Why does this make sense? The sample is taken at random, so it is representative of the population. All right, the sample has the same shape and a similar mean and standard deviation to the population. So the sample looks like the population. That's what it means to be representative. Right? In other words, when we take a sample, if it's taken at random, we're going to get a similar kind of mixture of households as what's in the population. We're not going to get mostly low income households. We're not going to get mostly high salaried households. We're going to get a mixture that's the same as what's in the population. All right, part H says, did anyone get a sample mean close to the high values in the population? The high values would be like 100,000 and above. And I can guarantee you that nobody would. The highest sample mean that anyone in the class got, we don't know, but probably not more than $75,000, I would guess. So it says, describe what would have to happen with the sample for someone to have actually gotten a mean that resembled the high values in the population. So if we got a mean, for example, as high as $150,000, there would have to be a lot of high salaries in the sample to get that kind of a mean. And they would have to get not so many low salaries. Whoops, this is in the sample. Sorry, hang on. That's a big difference. There'd have to be a lot of high salaries in that sample and not so many low salaries. Right? This wouldn't happen. Because the sample looks like the population. With mostly lower to middle salaries and a smaller number of high salaries. Right, so let me give you another example. Supposing we were interested in heights. Right, now, heights of human beings are generally normally distributed, right? And so you know what sort of an average typical height is for, say, a man, I think is maybe around 5 feet 10 inches. I'm not sure, I'm just making that up, but let's just say that's true. Right, if I were to take a random sample of men, let's say I took a random sample of 50 US men, I'm not going to get like 45 of them that are 6 feet 5 and taller, right? That wouldn't make any sense. There are people in the population that are that tall, but there's relatively few of them. So if I were to take a sample, I'm not going to get mostly really tall people and then a few sort of typical average and shorter people. That's not the way it would happen. If my sample's random and it's representative of the population, then my sample is going to look just like the population does. So in this case, I'm going to get a bigger hump of lower to middle salaries, and then I'm going to get a long right tail with a few higher salaries, and then the mean is going to come out similar to what it is in the population, and it's not going to be really high. All right, part I says increase the number of simulations so you have a total of 1,000. We'll look at the shape of the null distribution and see what that looks like. So we're going back to the applet, and I'm going to increase my number of samples now to 995 so that I'll get a total of 1,000. I already had 5 samples, and I have to just give it a second, and it takes all those samples of 1,500, which is really cool. And now what I have on the right-hand side in gray is a null distribution. So looking at these 3 graphs, the one on the left is a population distribution. It's right skewed. It has a mean of 72,641 and a standard deviation of 26,145. What I have in the middle is one sample distribution from the most recent sample. And it is right skewed. The one that's pictured now has a mean of 72,457 and a standard deviation of 24,944. But if I click around in the right-hand graph, I can pull up any other sample that I want to. So right now in the middle, I'm looking at sample 581 out of the 1,000 samples that were taken. And it's got a right skewed shape, and its mean is 73,120. And its standard deviation is 26,629. So in the middle graph is a sample distribution, and it comes from one single sample. Now what I have on the right-hand side is a null distribution. And that null distribution, notice, is not right skewed, it's actually bell-shaped. Now the mean is close to the population mean. The mean of my null distribution is 72,623. And the population mean is 72,641, so they're very similar. But notice the standard deviation of this null distribution is a lot smaller than the population standard deviation. It's only 690. That's a lot smaller than 26,000. So what happened, and why is this null distribution bell-shaped instead of being right skewed? Well, the null distribution is a distribution of averages, of means. And so we just got done saying that when I take a sample, my mean is not going to be very high, like 100,000, 150,000, 125,000. It's going to be more similar to the population mean. So when I look at the means, the averages from all these different samples, the average from those means is basically what the population mean is, but the standard deviation is a lot smaller because the means, the averages, don't vary that much. So in the population distribution graph on the left, the numbers along the horizontal, the 30,000, 60,000, 90,000, those are salaries from individual households. In the middle graph, sample distribution from sample 581, the numbers along the horizontal are salaries from individual households. But in the graph on the right, the null distribution, the numbers along the horizontal are average salaries from a group of 1,500 households. So I took 1,000 different samples of size 1,500, and each one of those 1,000 samples had an average. And those 1,000 averages are what's pictured in this null distribution gray graph on the right-hand side of the page. So the averages are bell-shaped. They're centered at whatever the population mean is, and then they deviate from that in this bell-shaped pattern. So the further away from the population mean you get, the less likely you are to have a mean that extreme. Okay, so let's go back to our worksheet. The null distribution is bell-shaped. So what does that mean? Most averages, right? Each dot on that null distribution dot plot comes from an average household salary from a sample of 1,500 households. Most averages are around, so these are sample averages, are around the population average. And then a relatively fewer number, few are lower, a few are higher. This is what creates the bell shape. If that null distribution was right skewed, that doesn't make sense because we would have to have gotten a bunch of samples with lower to middle salaries and then a few with high averages, and that's not what happens. So we would have had a lot of samples with low to middle averages and a few samples with very high averages, which is not what's going to happen. Right? Every time we took a new sample, the average was around the same as what it is in the population. All right, now we have to find a p-value. So the way we do that is using, remember, the count box. So we're going to put into the count box the sample statistics. So we have to, I should have made a note, we got to go back and look. What was the sample mean for Maria's sample? It was 54,398. Okay, so we're going to go into the applet and put in the count box the sample mean of 54,398. So remember, in general, when we're finding a p-value, we use the count box, and what goes into the count box is the sample statistic, in this case an X bar. Now, I hit Tab to see my whole graph was red. Well, something's definitely wrong there, right? So usually if my whole graph is red, that means there's a problem. So it's with this drop-down box. Remember that my alternative hypothesis, Maria's conjecture, was that the average household salary in her area of the country was less than what it is nationally. So I want the direction here in my count box to be also less. Notice this is less than or equal to, because the computer is counting how many out of the 1,000 simulated sample means that we got, how many were at least as extreme as less than or equal to the sample mean that was observed, 54,398. And as you can see, p-value is 0 out of 1,000. Notice that the farthest left number on the horizontal axis here is 70,000. So it would be highly unlikely to get an average even as low as 71,000, much less $54,000. Okay, so the p-value here is 0 out of 1,000. They want us to interpret the p-value. So the p-value, remember how we interpret that? The probability of what? Assuming what? So there is a 0 out of 1,000 chance of getting a mean household salary at least as low as Maria's sample mean, 54,398, assuming the population mean is, I gotta look it up, 72,641. Okay, so again, let's think about what we just did with the applet. We created a population where we assumed the mean really was 72,641. We made that assumption, and then we took a bunch of samples. We took 1,000 different samples and looked at what kind of sample means we might expect from a population that's right skewed with a mean of 72,641, and we never got a sample mean as low as 54,398, and we never got anything lower than that either. So it would be highly unlikely to get a sample mean that low if the population mean really was 72,641. Okay, and then they want us to evaluate the strength of evidence against the null hypothesis with a p-value of 0 out of 1,000. That is very strong evidence. Look at your chart, your strength guidelines on the formula sheet. That is very strong evidence against the null hypothesis. Okay, so what conclusion should Maria make about average household incomes in her area? So there is very strong evidence, and we want to make this conclusion about her research conjecture. There is very strong evidence that the average household salary for all households, again, we're talking about the whole population, for all households in Maria's area of the country, is less than 72,641. So again, notice that this statement is not about the sample of 1,500 households. We already know that average is less than 72,641, but we're trying to use that sample mean to make a conclusion about all households, even though the sample was quote-unquote only 1,500 households. So if we have very strong evidence against the null hypothesis, then we have very strong evidence in support of the alternative hypothesis. So we have very strong evidence against the average being 72,641, and very strong evidence that the average is in fact less than 72,641. Again, the word all and underlined is really important in this conclusion. We are making a conclusion about the whole population, not just the sample.